In order to understand the plan space, we have to think about what query plans would produce an equivalent answer to the query we asked. And so we're going to want to look at different ways that relational algebra expressions can be equivalent, even though they have, say, a different order of operations or otherwise are expressed differently. So let's start by looking at selections. And here are two rules of equivalence for selections. The first says that if you have a conjunction of predicates in your selection predicate, so here we have selection with the predicate C1 and ... and Cn, that is equivalent to a cascade of individual selections, one per predicate. So here we have selection of C1 over ... over selection of Cn over R. You can read the right-hand side sort of implementation-wise by saying we're going to scan R, and for each R tuple, we're going to filter it out for only those things that match Cn. And then we're going to take the results of that and filter it for only the things that match Cn minus 1, etc., until at the end we filter out things that only match C1. And you should be able to convince yourself that that's the same as filtering R for the conjunction of all those predicates at once. Another thing we can do with selections is we can commute them. Selection of C1 over selection of C2 is the same as selection of C2 over C1. Like selections, projections also have a cascade equivalence, but it works a bit differently. The general statement is that a projection can cascade to a superset of columns of the original projection. In our example here, we have a projective A1 on R being equivalent to a projective A1 on a projective something bigger, A1 through An minus 1 of R. This allows us to do partial projection lower down in the plan before we do the final projection higher up in the plan. Cartesian products have equivalences that should be familiar to you from grade school arithmetic in multiplication or addition. And the equivalences are associativity. R cross S cross T is the same as R cross S cross T. And commutativity. R cross S is the same as S cross R. Now, generally, we're more interested in joins than cross products because they're much more common in queries, and we have efficient algorithms for joins. So are joins associative and commutative? After all, they're just Cartesian products with selections, right? Well, you can think of them as being associative and commutative, but you have to be a little careful because joins sometimes will turn into cross product when you do this. So to make this clear, let's look at three tables here, R, S, and T. R and S share column A. S and T share column B. R and T don't share any columns. So we can have a query like the next one on the left here, which says S join T on column B, join R on column A. And we might want to try to apply an associativity rule, S join on column B, T join R on column A. So we just moved the parentheses around, but we actually created a query that's not even legal. T join R on column A is not a legal query. There is no column A in T. Now we might say, okay, fine, what we really meant was a natural join. So T natural join R is simply T Cartesian product R. So in this nested bullet here, we're showing a slightly different interpretation of the query, which says S join T cross R on B. But that's not the same query either because we've lost our predicate on A. So in this bottom row, we show the actual equivalence after associativity, which is that S join T join R is equivalent to S join T cross R, where the join is on both B and A, because once we've taken the cross product with T and R, we have both the attributes we can join with S. But T and R themselves don't have any attributes in common. And you can see, of course, that that thing on the bottom right might be inefficient because it has a cross product. So to show this in terms of query plans, here are 4 query plans for this query. And the query is actually in SQL in the upper right. And you can see that one of these 4 query plans, the one on the lower right, has a Cartesian product in it because it combines R and T together. But the other query plans, the other 3, all are simply equijoins, which we could use sort merge or hash joins for because they are combining tables that share columns. So be a little bit careful in your join ordering. Some join orders will have Cartesian products where other join orders won't.